Here are the graphs that you all need to be familiar with, okay? And again, here's what we're doing today. We're going to be entering data directly from what they've given us. Then we're going to graph those things, and we're going to look to see what does it look like the most. Does it look more like a line? Does it look more like a quadratic or an exponential function? Does it look more like a logarithmic? Once we determine that, then the next thing we're going to do is we're going to write this thing that we call the regression equation, or the line of best fit. And all that means is we're going to write an equation of the function that most mimics that data. And then we're going to use that equation to actually predict future values. It's very simple. It's all calculator. But these are what you need to remember. Lines. Lines are either going to be going up or they're going to be going down, but it's going to be very consistent. No curvature. Okay? Now listen, I know you got points like that, so obviously it's not going to always be a perfect line, but if it stays linear, then we're going to assume it's a linear equation. Quadratic, of course, you know, either looks like an upside down U or a U. The exponential functions either start real flat and then go real steep, or they start by coming down real fast and then they get flat. And then, of course, logarithmic, they start by going up real fast and then they level off. So these are the ones that you need to be familiar with, okay? When we look at our graphs, we're going to look at them and say, hey, which one does it look the most like? And then there's something that we can do to kind of test to see if we chose correctly. All right, so you've all reset your calculators, right? Okay, so let's get into your calculators, and let me just say, I'm going to try to show you guys all of these key presses, but they are also all in your notes. Okay, the notes are very good at kind of defining all the different key presses that you have to make to do all this, except for one, and we're going to start with this one. Okay, are y'all ready? When we run regression equations here in a minute, there is one piece of data that I like to look at. It's not a mandatory piece of data, but I like to look at it, and I'll tell you why in a minute. But the first thing I want to do is I want to turn it on, okay? So here's where you need to go in your calculator. Go over here to Mode, and I want you to scroll down to this thing called Stat Diagnostics, and I want you to turn it on. So scroll over to on and push enter. You won't find this in your notes. And the reason is it's not absolutely mandatory. But I like to look at it, and there's something I like to show you about it. So Stat Diagnostics on. Now, everybody got that done? Let's go to Stat. And we're going to edit. So let's enter this first group of data that they gave us. So my X column includes 0, 4, 7, 10, 12, and 15. I'm going to scroll over to the list 2. Remember, these are ordered pairs. 0 goes and matches up with what? So you got to put them in the right order or to mess it all up. So 085, 482, 781, 1079, 1277, and 1576. Now, I've entered all my data correctly. Remember, what did I tell you we want to do now? We want to look at it and determine, does it look more like a line? Does it look more like a quadratic? Does it look more like an exponential? Or does it look more like a logarithmic function? So we got to go graph it. Now, in the past, where have I told you that we go to graph? Y equals. Well, we're not going to quite go to y equals. We're going to go to second y equals. Go to second y equals. Because we got to turn our stat plot on. So go right here to plot 1. It says off. If you reset your calculator, enter on that and turn it on. Okay, has everybody done that? Stat plot on. Now, the last thing we're going to do to actually see our data is we're not going to push graph. And the reason we're not going to push graph is because when we're dealing with different data, remember, graph is just going to show you 10 to the left, 10 to the right, 10 up, and 10 down. We want to zoom in on our stat plot. So instead of pushing graph, I want you to push zoom. And I want you to scroll down to number 9, which says what? What does that say? Zoom in on your stats. That's what it's telling you. Zoom stat. So I want you to push enter on that, and boom, there it is. There's our graph. Now, look at your little plots that you kind of drew earlier, and you might not even have to. Just look at this one. What does it look the most like to you? It looks linear to me too, right? It would be a line that has what kind of slope? You need to go to the restroom? To put your contact back in? You want me to see if I have any solution? Okay. Okay, so this looks the most like a line. So I'm going to say this is linear. Okay, so write that down. It's linear. So we're going to actually skip a step, and we're going to go to what the notes below it tell you. Since we think this is a line, we're going to run a linear regression test. We want to write an equation that mimics this to the best of our ability. And since you guys think it's a line, we're going to go run a linear regression test. So here we go. Go back to your calculator, and these notes are just below this. Type in stat, but this time we want to go over and calculate. Now, remember we did this the other day, and we ran a one variable statistics to come up with mean and all that stuff? Well, we're not doing that. We're doing regression. Regression will write an equation that most mimics this data, which you guys think looks a lot like a line, doesn't it? So we're going to run a linear regression. Look at all these. See number 4? That's a linear regression, and it's in mx plus b form. That's the one we like. What do y'all think 5 is? Quadratic. Quadratic. Number 6 is kind of a no-brainer. Cubic. What do you think number 7 is? Quartic. Number 8 is another linreg, but it's just in a different format. No big deal. What do y'all think number 9 is?
Is that exponential?
ln. Logarithmic. That's logarithmic.
Where's exponential?
Go down one more. X reg. Number 9. So
we're only going to be using 4 different ones?
Yeah, we're gonna limit ours to logarithmic, exponential, quadratic, or lines. Okay? So y'all looked at the plot and y'all thought, hey, it's linear. So let's go run a number 4. And you can run a number 8. It's the same thing, it's just in different order. But I'm gonna run a 4 because we usually do y equals mx plus b, don't we? So here it is, number 4. Just push enter a couple times, calculate, and voila. It creates your equation for you. Look, it tells you your equation, y equals ax plus b. And then it tells you all the values you plug into those. Okay? So, let me write my equation real quick, and then I'm going to explain something. Y equals, what's A? Let's go to 2 decimals. What's A? Negative 0.61x. And then what's B? Plus 84.85. Okay, before I zoom back to this, let me show you guys something. If you did not turn your stat diagnostics on, you wouldn't have these bottom 2 values. They wouldn't be there. Okay? The only thing that would be there is all the way through A and B. That's it. So why did I want you guys to turn this on? Because of R. R is this thing we call our correlation coefficient. Our correlation coefficient. And all that means is, how well does this data correlate to a line? Okay, that's what R tells me. If I was running a cubic regression, R would tell me how well this data matches a cubic function. we want our R value to either be really close to +1 or really close to -1. +1 or -1 is perfect correlation. Now, y'all saw the graph. Was it a perfect line? It wasn't perfect. So therefore, it can't be a perfect regression, but it's really close. Look, it's -0.99. That's really close, okay? This line really does a good job correlating with this data. That's what R is about. So I like to run these with stat diagnostics on. That way I can see what my correlation coefficient is. The closer those values move towards 0, the less they represent whatever regression you ran. Do you understand? We want that value to be really close to 1 or -1. Yes?
So if you were to put it in like quadratic, then it would be really off.
It would be. Watch. I'll just show you since you asked. If I ran a stat, calculate, and I did a quadrag, that was actually R squared's 0.98. That's pretty solid still, actually. The R squared is. It doesn't give an R for quadratic. Let's do like a, and here's the explanation to that. Y'all know how a quadratic will just kind of do this? Maybe that data is representing the very bottom or the way down where it looks like a line. Let's see. Let's run a logarithmic one. You can't do that because of 0. We use a 0. Hang on. Let's run a cubic regression. R squared is 0.98, also very good. So this data really could be represented with some different things. Let's see, stat, calculate, because it could be catching different places of that. Let's try exponential regression. The R value is -0.992, also very good. Okay, and listen, I know it seems like it's a little bit of a backfire, but it's not. Here's what's actually happening here. When you talk about a line, right? If I'm looking at a quadratic, doesn't a quadratic come down like this and then go back up? So I could just be catching a piece of that graph. You see what I'm saying? So just that piece of that graph could be representative of a quadratic. Same with an exponential function. Doesn't an exponential function, can it come down like this right here? Well, again, I might be catching this bottom part of it. So again, you kind of have to look at the graph like we did and determine what it looks the most like. And in this case, it was a linear regression. So we're going to run a linear regression feeling pretty confident that's what it is. And we are confident because no matter what it is for the other ones, what's the R value for this? -0.99. That's solid, okay? So whether it could also mimic other things or not, doesn't matter. It looked more like a line. We ran a linear regression, and it was really good, okay? So we can feel really confident about that. All right. In fact, let me show you one other thing. Yeah, before we answer this question, let me go back to this. Go back to y equals, or let me do it, and y'all just look at it. Didn't we say our equation was -0.61 x plus 84.85? Isn't that what we said our equation was? Now, if we graph this line with that stat, look at this. How close does that line mimic that data? Really close, okay? Really close. So sure enough, I can feel pretty confident in this being a correct line for the data they gave me, even if there were other things that were good too. Y'all with me on that? So there it is. All right. Now you don't have to do that, but what you do have to do is, what does the next question ask you? What does it say? Next. It says use the regression equation to do what? So not only are we going to look at the data and determine what we think it is, and not only are we going to run the regression equations to come up with what we know the equation to be, but we're going to use that equation to predict future values. So how would I do that? How do I use this equation to predict what it's going to be at 22 feet? Anybody? How do we use this equation to predict? Yeah, you're going to plug 22 in for x. So you're going to go to your calculator, you're going to go negative 0.61 times 22 plus 84.85. That's how you use your equation to predict future values. You plug them in, and the equation will do the work. Okay, we're going to assume it's going to be really close to what value? Was it 71.43? And this was degree Fahrenheit. So that's going to be my prediction. It's going to be 71.43 degrees Fahrenheit. Questions about that?
Where'd you get that 70? Where'd you get that from?
That's when I in the reading. See how it says that the temperature T in degrees Fahrenheit? You mean where did I get 71?
Yeah.
I just plugged in 22. Look. Plug that equation in, negative 0.61 times 22 plus 84.85. We just plugged it in to try to figure out what it would be at 22 feet. Does that make sense? Okay, now let's go to the next one. The next two have a little trick to them, and that is when we're dealing with dates like this, years of like 1992, 1994, because in a graph, it takes so long to get over to 1992. Sometimes it's best to change these values for something like this, 1992, doing something like this instead. Years from 1990. Years from 1990. So for example, when I go to my calculator, and instead of plugging in the x value of 1992, what would I use instead? 2. Because that's 2 years from 1990. What would I use for 1994? 4. 1996? 6. 1998 is 8 years from 1990, and 2000 is 10 years from 1990. This allows your data to not be quite as skewed because you don't have to go so far on your x-axis to get to these values. And it'll give you a better spread so you can see your data a little more clearly. All right, so here we go. Let's go to our calculator. Let's go to Stat, Edit. And what I would suggest is you go up here and you clear, enter the list. Clear, enter. Don't delete, please. Don't delete it. Just clear it. So here we go. Let's enter this. So my years are 2, 4, 6, 8, and 10. What was year 2? 633. Year 1994 was 793, 1100, 1771, and 4696. So here's my data. Again, isn't my stat plot already on unless you reset your calculator? But what if it's not? What if it's not on anymore? Where do I go? Second, stat plot. Does it say plot 1 is on? Yes? Okay. So we're going to zoom in on our data, right? How do we zoom in on our data? Zoom number 9. And voila. There it is. Now, would you guys comfortably say that this is a line? Doesn't look linear to me. Does it look linear to you? So, according to the things that we just graphed, to you, which one does it look the most like? It looks more exponential, doesn't it? So I'm going to go with exponential here. All right? I'm going to go with exponential. So let's go run a regression equation for an exponential function. All right, so I'm going to go back to what? Stat. But this time I'm going to go over to calculate, and I'm going to run a number 0. Exp-reg. Exponential regression. Push enter a few times, and voila. Now, can we be pretty confident in this being exponential based on our data here? Why?
Well, it's 91.
Well, no, it's R. Look at your R. Your correlation coefficient is R. It's about 0.96, isn't it? 0.96 is pretty solid. Here, let me go back since we did this earlier. Let's go run a line test this time. What is the R value here? 0.86. Which one's better, 0.96 or 0.86?
It's just like in the 90s. Is that like how you know it's good?
The closer it is to either 1 or -1, that's what predicts whether it's a really good representation or not. So we're going to run what we thought it was, an exponential regression. So here it is. Let's go write our equation. So y equals A. What's A? Let's round to 2 decimals. That's going to be 280, right? So 320.28, open parentheses. What's B? Guys, are y'all here? 1.27 raised to the x power. So here's my equation, guys. 320.28 times 1.27 raised to the x. I can be pretty comfortable with that because my correlation coefficient was really close to 1. Next, use this equation to estimate the closing price in 2003. So here's the hardest question I'm going to ask you for this problem. Do I put 2003 in there?
No.
I put 13. Why 13? Exactly. We did years from 1990, and 2003 is 13 years from 1990. So go type in your calculator, 320.28, open parenthesis, 1.27, raised to the 13th power. And once you get that tallied up, tell me what it was. $7,161.07. And this was money. See, it's a closing price, so this is money. So $7,161.07. Okay? And that's all there is to it. All right? Now, the next two problems are even easier than these because, have y'all looked at them yet? What does 3 tell you in the reading? It tells you it's what? A logarithmic model. And number 4 tells you it's a what? So you actually don't have to graph it and look for yourself. It's specifically telling you, hey, we want you to run number 3 as a logarithmic one, and we want you to run number 4 as a quadratic one. Now, there is one trick to number 3, and it will skew our data if we use different numbers. Okay? So see how these are years again? So when it's 1970, 1980, 1985, 1990, 2006, what do y'all want to use here?
Do we not just use the regular number?
You can. It's just going to make your data a little bit off, I think, because it's so far over. We can try. Let's.
Go by 5 though, or by
You can. I would pick a date. Like years from what year? Years from, how up earlier we used 1990. What would y'all want to use here?
1970.
I wouldn't do 1970, and here's the reason I wouldn't do 1970. Some of your equations, if you plug x into 0, it could cause issues. So years from 1965. Y'all want to do that? I usually go a little more basic. I like I probably would have done years from 1950, but it'll work. Okay, so years from 1965. So how many years from 1965 is 1970? 5. How many years from 1980 is how many years from 1965 is 1980? 15. 85. 20. 90. 35. And then 2006 is how many? Might have to subtract. It's 41. 41. So these are the numbers we're going to use, okay? I'd be interested. I know your equation will be different if you use different years, but I don't know if the end result might not give you a very, very close prediction. I'm going to try it real quick. All right, so here we go. We got 5, 15, 20, 35, 41.
It's not 35.
1990? It's 25. You're right.
Yeah. I was like, what is that math?
Sorry. Do y'all see that mistake? That's a 25. 1990 is only 25 years from 1965. Okay, I got that fixed on mine. Fix it on yours if you haven't already. 30, 35.3, 37.9, 37.2, and then finally 41.5. Again, I don't have to go graph it. You can if you want. But they already told me I'm going to run a what? And which one is my logarithmic one? The ln. ln reg. Logarithmic. It's natural logarithmic, but that's the one we're going to run. So here it is. We got the equation y equals, what is my a value? Not all at once, please. 21.32 plus, what's my b value? 5.29 ln of x. I'm going to go back to my page, and this is what you should have if you use the same values that I used. 21.32 plus 5.29 ln of x. Now, last question for this problem. They want me to predict what it's going to be in 2016. How many years from 1965 is 2016? Huh? Subtract for me. 2016 minus 1965. 51. So we're using the value 51. So here we go. We're going to go 21.32 plus 5.29 ln of 51. So I'm going to go back to my calculator. Make sure you find all these. I'm going to type it in. 21.32 plus 5.29 ln of 51. Enter, and it gives me a prediction of about 42.12.
Is that the estimated population now?
That would be the estimated population in 2016, according to the data that we're working with. Okay? Questions about that? Go back to that page, so if you didn't write it, you can write it. My estimate would have been 42.12. Again, in my notes, I used different values, and my predictions were close to that. It was my predictions when I used different values was 43.5. This is 42.12. So you just have to realize it's going to be pretty close, but it might not be just dead accurate, depending on what values you use. Okay, last one. And the only thing about this one is, what is my table when it's left to right? Which one's X and which one's Y when it's left to right instead of up and down? You know, when it's up and down, X is on the left and Y is on the right. When it's side to side like this, which one's X and which one's Y? X is top and Y is bottom. Okay, so just don't forget that. So when I go back to my calculator and I go to Stat Edit and I clear my data, clear enter, I'm going to enter the top values into X. So my top values are 0, 0.5, 1, 1.5, and 2. My list 2 is going to be 50, 64, 70, 68, and 58. But this time, again, you can look at the graph if you'd like, but what does it ask you to do? It asks you to run a quadratic. So I'm going to go straight to Calc, and I'm going to run a quad reg. Okay, so here's my equation. Ready? Y equals ax squared. What's a? So negative 16x squared. Plus bx. What's b? Plus 36x. And then plus c, which is 50. So, on your paper, your equation should be negative 16x squared plus 36x plus 50. And what's the last thing they ask us to do? After 3 seconds. So we're literally going to go plug in negative 16 times 3 squared plus 36 times 3 plus 50. You're plugging 3 into x. So you're going to type all that in, and you get 14. Now what was this in? It was height, wasn't it? Height in, does it say? It originally was in feet, so it's going to stay in feet. It's going to be at 14 feet after 3 seconds, according to our data. Okay? That's our prediction. Any questions with this? This is pretty simple, pretty straightforward. So I know it's a lot of calculator work, so don't forget, if you can't finish all of your homework right now in class, you've got your Chromebook that has your calculator on it, okay, if you don't have your own calculator. So your homework tonight is this worksheet I'm handing out, and it's all 4 problems, which is not too bad.